Okay, position tolerance calculation. The only way to ensure tolerances are produced properly on assembled parts. The limit stack method it ensures the worst tolerance values will be assumed, and two formulas for many common tolerancing applications. There's the statistical methods. It's a square root of the sum of squares for all the tolerance values. And there's computer variation simulation. There's no reliable conversion factor between position tolerances and directly applied coordinate tolerances. So you need to run it through this formula. And this is another issue I have with what I see in industry is a lot of machinists will not understand how to calculate this. And then what they do is they round down their tolerances to a point where they know they will fit. So you're trying to hold it to a position of 5, and then they try to hold it to a position of 3, so they don't have to do any math. And it's kind of an issue. So it's a consistent thing in industry that all the machine shop owners are wanting their employees to be able to calculate this properly, so they're not overproducing higher tolerances than what the drawing actually says. Okay. A floating fastener condition. Okay, it exists when a fastener passes through multiple holes that do not fix the fastener location. So this is a bolt. Okay, you've got a fastener, you got several smooth clearance holes and a washer and a nut on the opposite side. They consider that a floating fastener, even though when it's cinched down, it's not moving, but the position can float somewhat when you disassemble this. Okay. All holes have a diameter larger than the fastener, and common to use same sized clearance holes in all parts, but that's not required. But good design would be that if you have multiple parts going together, the clearance holes are all going to be made the same size. Where you run into variations there is when you have custom made parts going in with parts that were perhaps made by different vendors, then it's whatever they designed. So it gets a little more complicated. Okay, and tolerance calculations use clearance hole and fastener MMC sizes. Okay, so the floating fastener condition position tolerance formula works like this. Okay, letter T, which is your tolerance zone, is H minus, so it's the tolerance position applied to all the holes. You got H, which is your hole size at maximum material condition. Okay, so if you have multiple holes, it would be probably whatever the smallest hole is at maximum material condition. And the fastener maximum material condition size, which is going to be a constant because there's one fastener going through. Okay, and so the floating fastener condition example, a position tolerance calculation. Okay, if we were given a specified hole diameter of 328 thousandths of an inch, and you have a tolerance of plus or minus 4 thousandths on that hole, and your fastener diameter is 312 thousandths, and it's at maximum material condition. Your solution is T equals H minus F. So you have T, which is your 324 thousandths, which is 328 minus your minus the 4 thousandths, which gives you maximum material condition, and then you subtract the size of the fastener. So your tolerance zone for this floating application, this would be 12 thousandths. So that would be the diameter that you would put in your GD&T frame if you're trying to build this assembly. And so you would have the position symbol, you'd have the diameter symbol, you'd have 0.012 as your tolerance, and then and then in this case you would have to have the M modifier for maximum material condition. And then we follow with your datums. Okay, so floating fastener condition, if you're solving for the hole size, here's your given. You have a tolerance of 12 thousandths. Your fastener is 312 thousandths at maximum material condition. Your solution would be H equals T plus F. So H is 12 thousandths plus your fastener size at maximum material condition, and it results in your tolerance of 324 thousandths. So you're just calculating it backwards from the hole size with this method, and they use the same values in the example, so you derive at the same position tolerance for your, this is what your hole size would need to be based off the fastener being 312 thousandths and a desired position tolerance of 12. Okay, fixed fastener condition. This exists when a fastener passes through multiple holes and one fixes the fastener's location. So in this example is a screw going through clearance holes into a tapped hole into a finished part. So it's not a bolt, it's a screw. Okay, that's fixed by threads or a pressed fit or a taper or another feature that prevents the fastener from movement. Only one part fixes the location, the other parts include clearance holes. And the position tolerance calculations use clearance hole and fastener MMC sizes. The difference in diameter between the clearance hole fastener is divided evenly between the position tolerances of the other two parts. Okay, so here's an example. We've got a clearance hole with a part being screwed into another part. So the fixed part of this assembly is that threaded hole in the one part isn't moving, it's fixed, unlike a bolt and nut washer setup. Okay, the formula for this is T equals H minus F divided by 2, because you're splitting the tolerance in this case between the two parts. T is the position tolerance applied to all the holes. H is the hole at MMC, size for clearance holes. And F is the fastener at maximum material condition size. Okay, fixed fastener condition example, position tolerance calculation problem. Okay, so if we're given the problem of a hole that's 296 in diameter, and our tolerance on that hole is plus or minus 3 thousandths, and our fastener is 250 thousandths at maximum material condition, so it's a 1/4 inch diameter fastener. And here's our solution. So T equals H minus F, and then you divide it by 2. So T in this case is 293 thousandths minus 3 thousandths. So it's 3 thousandths less than the hole size because it's at maximum material condition. And then you're going to subtract the 1/4 inch bolt size from it and divide it by 2. Our result is 43 thousandths divided by 2, which gives us a tolerance of 21 thousandths 5/10. Okay, fix fastener condition size when you're starting with the hole size instead of the fastener. Or I'm sorry, you're starting at the fastener and you want to determine the hole size. So our given is a tolerance of 21 thousandths 5/10, and our fastener is a 1/4 inch at maximum material condition, or 250 thousandths. And our solution is H equals 2 times T divided plus F. So we're going to go 2 times 21 thousandths 5/10, and then we're going to add a quarter of an inch to it, 0.25 or 250 thousandths of an inch. H equals 43 thousandths plus the quarter inch, which gives us a hole size, basic hole size of 293 thousandths. Okay, so these are the same values. The difference between these two examples is this one we're starting with the fastener size, and we know what our tolerance is that we want to hold, and you work backwards to determine the hole size. The other method was starting with the hole size and comparing that to the fastener. Okay, additional tolerance, which it's not the standard in the standard to call it bonus tolerance, but it's vernacular. So in the industry, when you're talking about quality departments and machine shops that are making parts, sheet metal shops, they consider it bonus, so they call it bonus tolerance. Okay, the tolerance value in the feature control frame applies when a controlled feature is produced at the maximum material condition size and when the MMC modifier is shown. It's allowed when the feature size departs from MMC. Additional position tolerance is allowed within the virtual condition as produced feature surface departs from MMC for the surface method. So the larger the hole, the more bonus you get. Additional position tolerance as related to AME departs from MMC for the axis method. An allowable position tolerance is equal to the specified position tolerance plus additional tolerance for the produced feature. So if your feature is 1,000th bigger than MMC, then you get an extra 1,000th of bonus. If it's 2 thousandths bigger than MMC, then you get 2 thousandths of bonus. So it's basically calculated off the physical part you're measuring. Okay, so allowable tolerance and hole position tolerance at maximum material condition. So here's this example. They've gone through the calculations and created a table to show you how much tolerance bonus you have at different hole sizes. So again, the hole still has to be made within its tolerance. So in this example, it's a 1/2 inch part diameter hole minus 0 plus 6. So that means there's a potential for up to 6 thousandths of bonus if the hole is made at its maximum size, which would be at least material condition, actually. So the bigger the hole, the less materials there. Okay, so the allowable position tolerance is either the sum of the specified tolerance and additional tolerance, or the difference between produced hole size and the virtual condition size. And additional tolerance is the difference between the produced hole size and maximum material condition hole size for the axis method. So if we look at our table, if I made my hole right at a 1/2 inch, which is the low of the tolerance for the 1/2 inch diameter hole, if I made it 500 thousandths even, my position has to be right on the tolerance, which is a diameter of 35 thousandths. As I depart from theoretically perfect at maximum material condition, you keep adding tolerance up until you hit the maximum, the maximum of your tolerance. So again, if I were to make the hole at 506 thousandths, then I have 6 more thousandths of position tolerance, giving me 0.041 allowable. So again, what would you do if you're making the parts? If you're having trouble holding the position tolerance, you'd start reaming them out bigger so that you have more tolerance. So that's kind of the end result of adding this in reality. Okay, additional tolerance on a pin position tolerance at MMC. The allowable position tolerance is either the sum of the specified tolerance and the additional tolerance, or the difference between produced pin size and virtual condition. Additional tolerance is the difference between the produced pin size and maximum material condition of the pin for the axis method. Okay, so coordinate measurements, and data collection. Measurement machines and inspection software, functional gauges, and manual measurements all can be used to find the position tolerance. The position variance is the difference between the basic dimensions and your measured values. And the variations from true position, referred to as the delta coordinates, or delta x and delta y and delta z. So the Greek letter for delta looks like a triangle. And here's the position calculations from coordinate measurements. Now, those who have taken some of the machine shop classes with me in ADVM 67, we calculate position. I used the same formula, but I used a different method to compare the tolerance. So you were taught to do this formula minus the multiplied by 2, and then we divided the actual tolerance number in half. Here they compare it a different way. It's the same comparison, just using a different lens. So I am going to discontinue teaching it the way I have been doing, but I had a slightly different formula, and this is a simpler format. But those that have taken classes from me before, I'm sorry if that confuses you, because the book uses a different method. But the basic formula is the same. It's just what's different is how we compare the tolerances on the inspection sheet. So we'll be teaching you to multiply the number by 2 as opposed to dividing the tolerance in half. Okay. So the coordinate measurements are used to calculate the diameter, position, tolerance consumed by the measurement hole. The measured coordinates are made relative to a datum reference frame, and the measured position variation diameter must be less or equal to the allowable position tolerance for the hole position to be acceptable. Okay, so here's a method called paper gauging. You basically plot the points on a template like this. The number of rings in the circles depends on the tolerance of the hole diameter. Okay, so in this case, in this example in the graphic on the left, you have a 188 thousandths diameter hole at maximum material condition, and its tolerance must be, let's see, 1, 2, 3, 4, 5, plus or minus 5 on the diameter. Okay, so if you're going to use this method, you would need to take that into account, how many rings. And what we're seeing on the left in the grid pattern is a hole number 1, 2, 3, and 4, where they actually fall in relationship to their datums. Okay. Okay, so it's a method of illustrating a position tolerance and actual position of a feature in a graph to determine whether the position is within tolerance. The point selected as the origin represents the true position of the measurement hole. So that's would be theoretically perfect. All hole positions are controlled by a single position tolerance plotted relative to. So in this example, I think we go over this example again, but just to reiterate, right now holes number 2 and 3, no matter what hole size the holes were drilled, are within tolerance because they're within the tolerance zone of the smallest ring. Hole number 1 would only be correct on its position if the hole was machined at 189 thousandths or bigger. And hole number 4 is only within tolerance if the hole was machined at I believe 191 thousandths in diameter. Okay, so the concentric circles are overlaid on the paper with the centers at the origin for plotting points.